Hi, and welcome to a presentation on financial topic models. In our work, we use topic models to gain insights about financial texts that can potentially affect the performance of stock prices. First, I want to start by introducing a case study, which is the motivation behind our project. This is the stock price of Apple Inc. over a 6-month period until October 2016. In our work, we are especially interested in significant changes in the stock price, which can be seen here. If we look at news articles that were published shortly before the significant negative trend, we find articles like the following that are related to the decreasing sales of iPhones. Similarly, we are interested in positive, significant changes as well. Again, if we look at news articles that were published shortly before the price trend, we find articles talking about the release of a new iPhone. From this case study, we make the following observations. After reading the news about certain events, like the release of a new iPhone, investors can make decisions based on these articles. In our work, we identify signals in the text that can potentially provoke these stock changes and combine them in a meaningful model. Ideally, this model should be able to predict the future performance of stock prices when new articles are published. Next, I want to briefly introduce some related work, which we grouped into 3 main categories. The first category are handcrafted, rule-based systems which make use of manually constructed, dictionary-based sentiment patterns. Also, events are extracted based on rules. The second category uses metadata in addition to the textual information. Since this work uses Twitter data, it is possible to take advantage of additional signals, like user relationships, for example. The third category is the most similar to our work, since these approaches also make use of topic modeling. These works usually combine topic modeling with feedback from a time series like stock prices to improve the topic model. In the following, I want to give a formal definition of the problem. As input, our approach requires documents and stock prices with daily timestamps. These timestamps fall into an interval that we can define depending on the amount of data that we want to analyze. The output are the predicted labels for all documents of day t. To keep our definition as general as possible, the labels can be of 3 types. Binary, indicating significant price change, multiclass, indicating a positive, negative, or neutral price trend, or they can be the prediction of the actual stock price itself, which is a much harder problem compared to the previous 2. In the following, I would like to give a high-level outline of our method. To account for the temporal dimension in our text data, we concatenate all documents for a certain company of a certain day. We then learn the document topic distributions theta using latent Dirichlet allocation. Since documents are ordered by company and day, it gives us the document topic distribution over time, which we can then link to a stock price in our model. In addition to topic information, we perform sentiment analysis on our corpus, where we find all positive and negative sentiment words for each document. The model is then learned using different machine learning algorithms with varying feature combinations. In addition, we use part of the data as a development set, which we use to tune parameters for our predictive model. After training and tuning the model, we will be able to classify unseen documents into binary classes. These 2 classes indicate whether a significant price change has happened in the stock price for the company that is related to the document. Finally, we evaluate our method on held-out test data and report various common evaluation metrics. For our classification task, we have identified the following features. As mentioned before, we obtained document topic distributions over time by grouping documents with identical timestamps for each company. We can then use the probabilities of the document topic distribution as features in our model. Here the intuition is that certain topics might be indicative of price changes that we hope our model to capture. For example, an indicative topic might be related to company acquisitions. The second feature makes use of the document topic distributions as well, but instead of the document distribution itself, the feature will capture the changes in the document distributions. These changes will be calculated as the difference in document topic distributions over the current day and the previous day, which is captured here as theta subscript delta. The intuition is that changes in topics could predict changes in the stock price. Lastly, we utilize a sentiment dictionary for sentiment analysis of every document. This dictionary is derived from SentiWordNet, which is a publicly available resource for sentiment analysis and opinion mining. For each document, we calculate the probability that it is positive or negative by looking at the relative word frequencies. Since words can have multiple meanings, we perform word sense disambiguation using the Lesk algorithm, which uses dictionaries for automatic disambiguation. Now I would like to introduce the three classifiers that we consider in our approach to learn the prediction model. Logistic regression learns a function of linear combinations of weights and features. This linear combination is transformed using the logit function to output a value between 0 and 1. This value can be interpreted as a probability that can then be split into the two classes that we desire for predicting whether a price change is significant or not. On the other hand, the support vector machine classifier constructs a hyperplane to separate the data points into different classes. It then maximizes the margin of these hyperplanes and the data points. In our experiments, we tried CSVM with linear, polynomial, and RBF kernels. If time permits, we will also try the naive Bayes classifier on a dataset. There are a number of hyperparameters to consider. For LDA, there is the number of topics k that have to be specified up front. In our experiments, we have performed grid search to find the optimal value for k. Currently, the approach considers only the changes between the current and the previous day as features. However, it would be interesting to explore the effect a larger window size would have on the method's performance. To incorporate multiple days, we introduced a decaying factor alpha, which puts less importance on documents that were published further in the past. The change in topic theta subscript delta can then be calculated as the current day subtracted by a linear combination of days where alpha is raised to the power of the distance between the current and the past day. We also need to decide whether to use stopwords or not. Since we use LDA for topic modeling, the effect of removing stopwords could be minimal, since they might be covered by one of the topics. Next, I would like to talk about the dataset that we have constructed and which forms the basis for our experiments. We have considered stock prices and news articles in a time frame that ranges between September 2013 and June 2016. In total, there are about 24,000 New York Times articles about 23 tech companies, like for example Microsoft or Google. After combining these articles by day and company, we receive documents for 6,208 days. Looking at the stocks for different companies, we obtain 1,507 days with significant price changes. We define a change as significant if it is larger or equal to 2%. My teammate Irene will now present the remainder of this slideshow.
In the next section, I will talk about our experiments, evaluation results, and analysis. First, I will briefly introduce our evaluation framework. Due to the imbalanced nature in our dataset, where the significant changes over 2% in stock prices are rare, we have far more negative instances than the positive ones. So we randomly sample the same number of negative instances as the positive ones. We repeat the sampling 5 times and take the average of the results. For the dataset, we keep 1/6 data held out as a dataset for hyperparameter tuning and do the 5-fold cross-validation on the rest. Our evaluation metrics include accuracy and precision, recall, and F1 score on positive class, since our focus is to predict the significant change over the stock prices. Here are some results for our experiment 1. In this experiment, we firstly do the topic modeling in one company, Microsoft's corpus. where we have 180 instances. We run the sampling and classification with logistic regression 5 times. The results are reported in the table. There are some problems with such experiment setting. First, the corpus is too small for topic modeling and the classifier, so the results are not representative or reliable. Also, such a method would be incapable to be extended to deal with those companies which are only mentioned in a small number of documents. Furthermore, by modeling for each company independently, we are actually ignoring the correlation among the corpus for different companies and thus may lose a lot of useful information. Given the two major problems mentioned above, we further make modifications to our experiment. First, we would combine the corpus for different companies as one huge collection for the topic modeling and the classification task. In this way, first we can have a larger dataset so that our results will be more robust. And also, we can run the topic model in the large collection across different corpus so that we could gain more informative topic distribution. Furthermore, we would try different feature combinations, and the results are reported in the following slides. This table shows the SVM results with respect to different number of topics, from topic 10 to 50 topics in the LDA part. Each row in this table are the best performances of all the feature combinations given the number of topics. By the best performances, we are referring to the highest FN score. Accuracy here is not our priority because our objective is to predict the significant change in the stock price, so only the true positives are of our key interest. We can see from this table that with the growing number of topics, the performance improves to some extent and then drops a little bit. So the best performance is where we have 40 topics. We have the highest FN score and the highest accuracy. This table shows the SVM results with different feature combinations. Here we keep the number of topics to 40. The features include 3 types mentioned before, including topic distribution, the changes in the topic distribution, and the sentiment words. We could see from this table that the best performance comes from the combination of the 3 features. We will do more detailed analysis in the following slides. From the previous result, we could see that the number of topics have a significant influence on the results. Our best performance comes with the number of topics equals to 40. Our assumption is that with too small number of topics, the coverage of each topics are too general and the topics distribution as a feature are not discriminative enough. With too many topics, however, we still could notice a drop in the performances. And our assumption is that maybe the topics are too specific and the good topics may get split. And another assumption is that for the large number of topics, we will have a larger feature dimension, so the current training data may not be enough to fit the model. As for the features, it is kind of surprising when it comes to topic changes, because intuitively, topic changes should at least be as important as topic distribution, if not more important. However, in our experiment, results shows that topic changes are not reliable as an independent feature at all, and it doesn't always help as a complementary feature. Still, intuitively, it should be a very informative feature when dealing with the time series. So our assumption is that we need more complex approach to handle the changes in topics over time. Another feature is the sentiment words. Even though it is just a three-dimensional feature with the probability of the positives, negatives, and the neutral words, it appears to be an effective complementary feature. Apart from the experiment mentioned above, we're also gonna do the evaluation on the different classifiers, including the logistic regression and naive Bayes, and also different hyperparameter settings, including the hyperparameter mentioned above and different sentiment thresholds, and also run the significant tests. Further results and analysis will be presented in the final report. In the previews of our experiments and exploration, we constructed two baselines to predict the significant changes in the stock price by leveraging the topic modeling and the classification task. In the future work, we want to construct stronger predictive model. The first possible solution is to incorporate time dimension directly into the generative model. So one possible solution is to do the topic model with time dimension and the event significant indicator. And the second direction is to learn from the idea of leveraging time series feedback for the better topic modeling. So one possible solution is to jointly improve the topic model and the predictive model at the same time. Here is a brief summary for our project. Our objective is to study the correlation between the topics from the textual data and the changes in the stock price in order to make further predictions. Our method is to first generate the features from the textual data with topic modeling, and then construct the predictive model by turning the original problem into the classification problem. We have built the data-driven baselines for the further exploration. Thank you for your attention. Please let us know if you have any feedbacks or suggestions.